Welcome to The Explainer. Today, we're going to dive into a pretty mind-bending mathematical idea that's quietly changing the game in everything from robotics to biology. It's a powerful approach that asks us to forget everything we think we know about flat, straightforward worlds and instead to embrace the curve. So, think about this for a second. Robot navigation, the special effects in 3D movies, and figuring out the structure of proteins. I mean, what could those possibly have in common, right? Well, it turns out they all depend on this fascinating problem-solving method that forces us to ditch our intuition about flat spaces and straight lines and to start thinking in a world that is fundamentally curved. Okay, so to really get a handle on this, let's start with a concept you're probably already familiar with: optimization. It's really just a fancy way of saying finding the best possible solution. You can think of it like a hiker who's trying to find the absolute lowest point in a giant, hilly landscape. Now, you can basically think of this in two flavors. You've got your standard optimization, which is like our hiker in a wide open field. They can wander anywhere they want to find that lowest point. But, in the real world, things are usually trickier. We have what's called constrained optimization. Imagine our hiker is now on a mountain, and they're only allowed to walk on very specific trails. Those trails, those are our constraints. For instance, in a computer problem, a trail might be a rule that says your solution has to be a valid 3D rotation. You can't just pick any random numbers. And this is where things get really cool. This is the core idea of this whole explainer. What if those annoying constraints, those trails on the mountain, weren't constraints at all? What if, instead, they were the entire world? This is where we bring in the hero of our story, the smooth manifold. Now, don't let the name scare you. Just think of it as any smooth, continuous surface, like a sphere or a donut shape, with no sharp edges. And the really cool thing about it is, if you zoom way, way in on any tiny little patch, it looks totally flat. And the source material has this absolutely perfect analogy for this. Imagine an ant walking around on a giant beach ball. From the ant's perspective, the surface of that ball is its entire universe. It doesn't feel like it's following a rule or a constraint. It just feels like it's walking on flat ground. And that simple shift in perspective is a total game changer. So this is the big switcheroo, right? The game-changing insight. Instead of trying to solve a really hard, constrained problem in a simple, flat world, we flip it. We solve an easy, unconstrained problem, but we do it in a more complex, curved world. The constraint isn't a rule anymore. The constraint is the space. Okay, so you might be thinking, great, we're in a curved universe. Now what? How do we actually find that lowest point when all our old tools were built for flat ground? Well, we need a new toolkit. We basically adopt three fundamental ideas. First up, we got to figure out which way is downhill. On a curved surface, that's not so obvious, right? We have to find the steepest path along the surface. Second, we have to completely rethink what a straight line even is. I mean, the shortest path between two cities on a globe isn't a straight line, it's an arc. Same idea here. And finally, and this is super important, we have to make sure that when we take a step, we actually stay on the surface. You can't fall off the beach ball. And that is the magic right there. That's the beauty of manifold optimization. By just embracing the natural shape, the geometry of the problem, we don't just solve it, we completely transform it. We take what was a tangled, complicated mess and turn it into something way more elegant and simple. So you might be wondering if this is all just, some abstract math toy. But no, not at all. It turns out this is at the very heart of some of the most exciting stuff happening in science and technology today. This approach is the engine behind a ton of different applications. Take robotics, for example. It helps a robot do two things at once: build a map of a new place, and at the same time, figure out where it is on that map. It's a classic chicken and egg problem. Or in biology, and this is amazing, it's used to piece together the complex 3D shapes of proteins, which is absolutely critical for developing new medicines. And the list goes on. Data science, computer vision, you name it. And, the source material really hammers this point home. This isn't just some clever trick for a few niche problems. This geometric way of looking at things has become a super powerful, widely used framework that's made huge waves in machine learning, robotics, and so much more. All right, let's pull all of this together. What's the big idea you should walk away with after this explainer? What's the main takeaway from all this talk about curved universes? The fundamental lesson here, really, is that sometimes the most brilliant solution isn't about trying to break down the walls of a problem. It's about realizing that the walls are the building. By embracing the constraints and making them the very world you operate in, you can unlock simpler, more direct, and often much more powerful solutions. And that leaves us with a really powerful final thought. This whole mathematical idea is kind of a metaphor for problem solving in general. It really makes you wonder, doesn't it? What other tough problems, maybe even outside of math and science, could be cracked if we just stopped fighting the rules and started seeing them as the actual shape of the world?